In our next section, we're going to learn how to anti-differentiate if we have problems that have products or quotients, basically anytime we have compositions of functions. There is no quote-unquote chain rule for antiderivatives. There is not a product rule for antiderivatives that'll solve every product, and there is no quotient rule for antiderivative. So I'm going to show you several different what they call substitution methods in order to solve composition of antiderivatives. So the first two I'm going to do first thing I'm going to talk about is composition. We end up with an outside function and an inside function. Okay. Typically the inside function is inside parentheses or in an exponent or underneath the square root symbol or in the denominator of a fraction. So those are the types of things we want to be looking for. And what we're going to do is we are going to look for an inside function. So step one is find an inside function that has the derivative of the inside function somewhere else in the integral. So, for problem number one, I'm going to find an inside function that has its derivative somewhere else in the integral. The first problem is the integral of 2 times 2x plus 1 cubed dx. If we did not want to use substitution, I could cube this using Pascal's triangle and multiply the result by 3, and then I could take the antiderivative of it, and it'd be no problem. However, if this became, instead of a 3, a 31, that would no longer become a problem, that would become a semester project. You'd have to basically multiply 2x plus 1 31 times, and even using the Pascal's triangle shortcut, it's still going to take you quite a while. So what we're going to do is find the inside function that has the derivative somewhere else. I told you most cases inside functions are in parentheses, exponents, underneath roots, etc. Well, let's look at this. 2x plus 1 is its derivative somewhere else in the problem. And it's okay for the derivative to be off by a constant multiple, but in this case its derivative is there. The derivative of 2x plus 1 is 2. So what I'm going to do is I'm going to do a substitution, and when I find that inside function, I'm going to go u equals the inside function. So I'm going to write u equals 2x plus 1. Step 2 is we are going to find du over dx and then multiply both sides by dx. So that means find the derivative of this function. So the derivative of u with respect to x is du over dx. The derivative of 2x plus 1 with respect to x is 2. Then you can multiply both sides by dx. That gives me du equals 2 dx. You may perform both of these steps at the same time, immediately writing the differential dx on the right-hand side. Your third step is to substitute for u and everything else. So now we are going to substitute. Okay. I'm going to actually do something a little bit different. Step 3, we are going to solve for dx. This is going to make some of our other problems easier. So to solve this for dx, I'm going to divide both sides by 2. and I get dx equals du over 2. Now I'm going to substitute. I'm going to substitute for my u and my dx. So u, 2x plus 1 is equal to u. So this is going to become a u. And then my dx is equal to du over 2. So this dx becomes a du over 2. So I now have the integral of 2u du over 2. Actually, 2u to the 31st. Sorry about that. Forgot that. Which is equal to the integral of u to the 31st du. Okay, so on this substitute step, I'm also going to put the word simplify. Step 5, find the integral with respect to u. Well, this is one of our memorized integrals. It's something to a power. So I'm going to add 1 to the exponent, divide by the new exponent. So I get u to the 32nd over 32. Last step, replace u with what it was equal to. So u is equal to 2x plus 1. So my final answer is going to write 2x plus 1 to the 32nd over 32. Okay? Find an inside function, take its derivative, solve for dx, substitute and simplify, take the antiderivative, and substitute what u was back into the original equation. And the way you can check your answer is you can actually take the derivative of this. This would be 32, 2x plus 1 to the 31st power, 32 over 32 cancels, times the derivative of the inside function, which is 2. And that does give us back to our original equation. Okay, so step 1, find an inside function. Well, this inside function is actually the exponent. So I'm going to write u is equal to 10x. Then I'm going to take the derivative and multiply both sides by dx. The derivative of u is du over dx. The derivative of 10x is 10, and move the dx over. Solve for dx, and I get dx equals du over 10. Make your substitution. This is going to become u, and dx is going to become du over 10. And that gives me, after substitution, the integral of 10 e to the u du over 10. The 10's cancel. That gives me the integral of e to the u du. Well, the integral of e to the u is e to the u. Except I can't leave my answer with u's. I need to substitute what u is equal to, and my final answer is e to the 10x. And because these are indefinite integrals, I have to add the plus c. So down here, I needed to add a plus c to my final answer. Okay, and again, I was able to do that substitution because its derivative was out here. The next problem, I'm going to look for an inside function whose derivative is in the problem. Well, inside function, think inside parentheses. Well, I have x to the 5th plus 6. What's its derivative? Well, it's 5x to the 4th. Is its derivative in the function? Yes, it is, but it's off by a constant factor. That's okay. It can be off by a constant factor. So, my u is x to the 5th plus 6. du is equal to 5x to the 4th. This is over dx. Bring the dx over here. Next step is to solve for dx. So I get dx is equal to du over 5x to the 4th. I forgot my dx over here. Now I'm going to make my substitution. This part is u, and dx is equal to du over 5x to the 4th. Substitution, I'm going to end up with the integral of x to the 4th, u to the 9th, du over 5x to the 4th. Which is simplified u to the 9th over 5 du. I am now going to take the antiderivative. I'm going to add 1 to the exponent, divide by the new exponent, which is 10. 10 times 5 is 50. I am now going to substitute back in for u. And add my constant. So I need to find an inside function and an outside function, or an inside function and its derivative. Well, remember that cosine cubed x is actually cosine x cubed. So anytime that you see this, you can think of it like this. So do I have the derivative of cosine in here? Well, the derivative of cosine is negative sine. Well, I have a sine times negative 1. It's okay to be off by a constant multiple. So I'm going to let u equal cosine x. du is equal to negative sine x dx. Solve for dx, and I get dx is equal to du over negative sine x. Do my substitution. Where I have a cosine x, I'm going to put a u. Where I have dx, I'm going to put du over the negative sine x. So that leaves me with the integral of u cubed sine of x du over negative sine of x. The sine of x cancels. I'm going to bring the negative out front. So it's negative the integral of u cubed du. I can now evaluate this. So I'm going to end up with negative u to the 4th over 4. Substitute back in for u. U is cosine of x. So my final answer would be cosine to the 4th of x over 4 plus c. Notice in each of the first 4 cases, the derivative or the derivative off by a constant function was inside of these. And the inside functions that became our u's were readily self-apparent. I'm going to pause the recording for a second. I'm going to write 4 more problems on the board and do some more examples. The only way to get good at u-substitution is to practice lots of them. Okay? And you will start to see patterns. For example, you should notice that I'm always dividing by, so here I divided by the derivative of the inside function. Here I divided by the derivative of the inside function. Here I ended up dividing by the derivative of the inside function. Okay? If they are linear terms inside as part of the inside function, that will always work. Okay? So when I did the examples on solving antiderivatives before, and we had problems like this one and like this one, I was able to do those, and I told you I would show you this week, and that's where they come from. So if you have linear terms as part of your inside function, we're going to actually write a shortcut in our next lesson. So I'm pausing for a quick minute, and then we will go on. So the next 4 problems are a little more difficult. We actually have to do a little bit of thinking first. Notice 4 and 5 are identical. They are the integral of x over the square root of x plus 1 dx. I'm going to solve it 2 different ways by making 2 different substitutions. In general, I told you to find the inside function. Well, there's 2 different ways to think about the inside function. The first one is making x plus 1 my inside function. Do I have the derivative of x plus 1 inside my problem? Yes, I do. It's 1. Okay, so let's do that. I have u is equal to x plus 1. So du is equal to dx. So let's kind of look at what I'm going to have here. When I do my substitution, I'm going to get x over u dx, which is du. So this is going to be a u. This is going to be a du. I still have an x that's unaccounted for. You need to get rid of that x. You cannot have any x's in your problems when you are doing integrating with respect to u. Well, I have something that x is equal to. I can subtract 1 from both sides and get x is equal to u minus 1. Now I'm going to end up doing 3 substitutions. This is u minus 1. Let's rewrite it now with my substitutions. That gives me the integral of u minus 1 over u to the 1/2 du. I am now going to break this up into 2 separate fractions, like we did during our last homeworks. So u over u to the 1/2 is u to the 1/2 minus 1 over u to the 1/2 is u to the negative 1/2 du. And now both of those are memorized integrals or antiderivatives. So I'm going to add 1 to the exponent, divide by the new exponent. I'm going to add 1 to the exponent, divide by the new exponent. And now I'm going to substitute back in for u, where u is x plus 1. Okay. I'm actually going to factor this first. No, we're going to leave it in this form. Nope, I'm going to factor out a 2u to the 1/2. So I have 2u to the 1/2. That's going to leave me with a u minus 1 here. And then I'm going to have a 3. It's actually u over 3 minus 1. Now I'll substitute in for my u. And I get 2x minus 1 to the 1, or x plus 1 to the 1/2 times x plus 1 over 3 minus 1. And that would plus c. If I didn't pull that factor out, I don't know which way your book has it. My answer would have been 2 times x plus 1 over 3 minus 2 x plus 1 to the 1. I would accept either one of these 2 answers, plus c, on a test. So that is the first method that you could have done that problem, where I substituted x plus 1 in. The second substitution that I am going to do is I am going to let u equal the square root of x plus 1. Calling this whole thing my inverse function is equal to the square root of x plus 1. Well, if I square that, I get u squared is equal to x plus 1. Okay? I'm going to solve for x because I'm going to have to substitute for an x up here, and I get x is equal to u squared minus 1. Solve because I did the same thing I did there. I am now going to take my derivative. Well, I can take the derivative here or here, as long as, let's figure this out. So this would be dx equals 2u du. Notice how it's already solved for dx, because the derivative here is 0. And I can do some substitutions. I have a substitution here. That becomes a u. Have a substitution for x. That becomes a u squared minus 1. And have a substitution for dx, which becomes 2u du. Notice my u's are going to cancel, and I would end up with 2 times that. And I can pull the 2 out in front. And that's what I'm going to do. So I'm going to end up with the integral of 2 u squared minus 1, and what's times u over u du. My u's cancel, so I end up with 2 times the integral of u squared minus 1 du. Do this in 2 parts. It's 2 times u cubed over 3 minus u. Now do the substitution, and I get this answer. Because what's my u? It's the square root. That's x plus 1 to the 1 half. X plus 1 to the 1 half times 3 is x plus 1 to the 3 halves over 2/3. And that's x plus 1 to the 1 half times the 2 out in front. So you get the same answer both ways. Okay? Some of these get a little more difficult, so you play around with them. Do problems. Anytime you do a new, maybe trick, make sure you have a note of how you did that type of problem. Next one. If only that was just an x squared, I could take that because that is the memorized. If that was just 1 over 1 minus x squared, that would be the memorized inverse sine function integral. Well, what do I need to put in, make u equal to make u squared right here? Well, let's think about it. What do I have? I want u squared to equal 16x squared. Okay, so what's u actually equal to? Well, u is equal to 4x. Now take the derivative of both sides of this, and you get du is equal to 4dx, or dx is equal to du over 4. And now you can make your substitution. You end up with the integral of 1 over the square root of 1 minus u squared. Where dx goes, I write du over 4. I can now take the antiderivative. It's going to be 1/4 inverse sine of u. Substitute back in for u, and I get 1/4 inverse sine of 4x plus c. So if you have something that looks almost like one of your memorized integrals, use the substitution to turn it into one of your memorized integrals. So this next one, the memorized integral, would be 1 over 1 plus x squared. which would be the inverse tangent function. So what I'm going to do is I want to make this 1 plus u squared, because the 4 can come out in front. So I want u squared to equal 9x squared. So u is equal to 3x. And now I'm going to be able to make my substitution. The derivative of u is 3 dx. So dx equals du over 3. I can now make my substitution. I can substitute for 9x squared and for dx. So I end up with 4 times the integral of 1 over 1 plus u squared du over 3. The antiderivative of 1 over 1 plus u squared is inverse tangent of x. So I end up with 4/3 inverse tangent of u. Substitute back in for my u, which was 3x, and you have 4/3 inverse tangent of 3x plus c. Again, I cannot warn you enough. The only way to get good at u-substitutions is to do all of the homework problems I assign for u-substitutions. So it's going to be a day or so until I get the even homework answers up, but they should be up in time for you to check them before this homework assignment will be due before your next test. If you get stuck on any of these u-substitutions, make sure you check out the Complete Solutions Manual. If you cannot understand the work from the Complete Solutions Manual or from the videos after I post them, please see me in class before school, during break, or during tutoring so that we can go over these. You will be doing u-substitutions frequently to solve antiderivatives for the rest of the year. Okay? Say these steps in your head as you go through the antiderivative process. It will make it a lot easier. You'll ingrain the steps that you need to do. These last few, we actually had to kind of think about to make things work right. Remember what your memorized antiderivatives are. Try to turn things into things that look like your memorized antiderivatives. So I made that 1 minus u squared. That one was easy. Hey, I pulled that 4 out. That was 1 plus u squared in the denominator there. That made that one fairly easy. Practice. That's the best way to get good at these.